Today we are going to discuss the absolute and uniform convergence of power series. First of all I want to define here the power series. A series of the form summation n equal to 0 to infinity a n z minus z naught power n. This is equal to a naught plus a1 z minus z naught plus a2 z minus z naught whole square plus up to so on plus an z minus z naught power n plus up to so on is called a power series. Where z naught and the coefficients an are complex constant. And z is a complex variable. Full stop. Also z naught is called the center of the power series. If the center of the power series is 0, that is z naught equal to 0 in equation first, then we have summation n equal to 0 to infinity a n z power n. This is equal to a naught plus a1 z plus a2 z square plus up to so on plus an z power n plus up to so on. So this is equation number second and this is equation number first. As we know that the power series is a tool in the field of real analysis as well as in complex analysis and many other branches of science and engineering. Here the main importance of the power series is the convergence. Now I want to define the absolute convergence of the power series. For this, a series of complex number converges absolutely if the series of absolute values of those numbers converges. The following theorem concerns the absolute convergence of the power series. So theorem first. If a power series summation n equal to 0 to infinity a n z power n converges when z equal to z1, z1 equal to not 0, comma, then prove that it is absolutely convergent at each point z in the open disk mod of z is less than mod of z1. Proof: let the power series summation n equal to 0 to infinity a n z power n converges when z equal to z1, that is summation n equal to 0 to infinity a n z1 power n converges z1 equal to not 0. Consequently, the terms a n z1 power n are bounded. That is mod of a n z1 power n, which is less than equal to m, comma, where m is some positive constant. N equal to 0, 1, 2, 3 and so on. If mod of z is less than mod of z1, this implies that mod of z by mod of z1, which is less than 1. This implies that mod of z by z1, which is less than 1. This implies that rho is less than 1. So this is equation first, where mod of z by z1, this is equal to rho C. Now mod of a n z power n, this is equal to mod of a n z1 power n into mod of z by z1 whole power n, which is less than equal to, from equation first, mod of a n z1 power m, this is m, mod of z by z1, that is rho power n, where rho is less than 1. This implies that summation n equal to 0 to infinity mod of a n z power n, which is less than equal to summation n equal to 0 to infinity m into rho power n. Now the series whose terms are real numbers m rho power n which is a geometric series and convergent. For rho is less than 1. Hence by comparison test, for the series of real number, the series summation n equal to 0 to infinity mod of a n z power n converges when mod of z is less than mod of z1. Hence proved. Next, I want to define some basic concept of the power series. First is region of convergence. Second is circle of convergence. Now first of all, I want to define here the region of convergence. The set of all points inside some circle about the origin is therefore a region of convergence of the power series. Next, I want to define the circle of convergence, the greatest circle about the origin such that the series converges at each point inside is called the circle of convergence of the power series. Next, suppose that a power series about the origin has the circle of convergence mod of z equal to r. Circle of convergence mod of z equal to r. And let Sz be the sum of the power series summation n equal to 0 to infinity, that is Sz. This is equal to summation n equal to 0 to infinity a n z power n, and this is a naught plus a1 z plus a2 z square plus up to so on plus a n z power n plus up to so on. This is summation n equal to 0 to n minus 1 capital N minus 1, here a n z power n plus summation n is equal to capital N to infinity a n z power n, and this is equal to Sn z plus rho n z, or Sz is equal to this, where Sn z is the partial sums of the power series. Nth partial sums and rho n z is the remainder after n terms of the power series. This implies that rho n z, this is equal to sz minus sn z for mod of z is less than r. Since the power series converges for any fixed value of z when mod of z is less than r, we know that the remainder rho n z approaches to 0 for any z as n tends to infinity. That is, rho n z tends to 0 as n tends to infinity for all z. Then by definition of the limit of sequence, this means that corresponding to each positive number epsilon, there exists a positive integer n epsilon such that mod of rho n z, which is less than epsilon, whenever capital N is greater than n epsilon. When the choice of n epsilon depends only on the value of epsilon and is independent of the point z taken in the specified region within the circle of convergence, the convergence is said to be uniform in that region. Now I want to prove the next theorems, theorem seconds. If z1 is a point inside the circle of convergence, mod of z equal to r of a power series summation n equal to 0 to infinity anz power n, then that series is uniformly convergent in the closed disk mod of z, which is less than equal to mod of z. Proof. Proof. Let this is my x-axis and this is my y-axis, x dash, y dash, and this is the closed disk and this is my open disk. capital R with the radius of the open disk. Let Z be any point within this closed disk and Z1 be a point on the boundary of the closed disk. For the uniform convergence, let small m and capital N denote any two positive integers where m is greater than capital N, and we write the remainder of the power series summation n equal to 0 to infinity a n z power n in the form rho n z. This is equal to limit m tends to infinity summation n is equal to capital N to m a n z power n. Say this is equation number first. Because there are many points whose modulus greater than mod of z1, for which the power series summation n equal to 0 to infinity a n z power n converges. Here we see that Z1 is the point on the boundary of the closed disk, and here there are many points. If we take this point we here, or the point another point be here, or another point be also here, then we see that the modulus of these modulus of these quantities which are greater than the modulus of Z1s. So as we know that if a power series summation n equal to 0 to infinity a n z power n converges when z equal to z1, z1 equal to not 0, then it is absolutely convergent at each point z in the open disk mod of z is less than mod of z1. Therefore, summation n equal to 0 to infinity mod of a n z1 power n converges. The remainder after n terms for this series is the non-negative real numbers and is given by sigma n. This is equal to limit m tends to infinity summation n is equal to capital N to m mod of a n z1 power n. Say this is equation number 2. From equation number first we have mod of rho n z this is equal to limit m tending to infinity mod of summation n is equal to capital N to m a n z power n. Say this is equation number 3rd. When mod of z is less than mod of z1, less than equal to mod of z1, we have mod of summation n is equal to capital N to m a n z power n. This is less than equal to summation n is equal to capital N to m mod of n into mod of z power n, which is less than equal to summation n is equal to capital N to m mod of an. Here we see that mod of z is less than equal to mod of z1, so apply here. We get mod of z1 power n, and the value of this quantity becomes summation n is equal to capital N to m mod of an z1 power n. Taking the limit as m tends to infinity, on both sides comma we have limit m tends to infinity mod of summation n equal to capital N to m an here z power n, which is less than equal to limit m tends to infinity summation n equal to capital N to m mod of an z1 power n. Using equations second and third, we have in the above we have mod of rho n z which is less than equal to sigma n. Say this is equation number 4. Whenever mod of z which is less than equal to mod of z1. Since sigma n be the remainder of the convergence series, so sigma n tends to 0 as n tends to infinity. Say this is equation number 5. Then for each positive number epsilon there exists an integer n epsilon such that sigma n which is less than epsilon whenever capital N is greater than n epsilon. So this is equation number 6. Hence from equations 4 and 6 we have mod of rho n z is less than epsilon whenever capital N is greater than n epsilon. So this is equation number 7. Now equation 7 holds for all points z in the disk, mod of z is less than equal to mod of z1, and the value of n epsilon is independent of the choice object. Which is the required condition for uniform convergent. Hence, the convergence of the power series summation n equal to 0 to infinity a n z power n is uniformly convergent in the closed disk. Hence proved. Note, an important consequence of this theorem is that the power series summation n equal to 0 to infinity a n z power n represents a continuous function sz at each point interior to its circle of convergence. That is if Z1 is a point inside the circle of convergence mod of z equal to r Then for each positive number epsilon, comma, there is a positive number delta such that, or we can say that there exists a positive number delta such that mod of sz minus s of z1, which is less than epsilon, whenever mod of z minus z1 is less than delta. The number delta being small, enough so that in the domain of definition mod of z is less than r of sz.